Hello and welcome to Launchpad Astronomy. I'm Christian Reddy, your friendly neighborhood astronomer, and in my day job I'm also a professor at Towson University where I teach astronomy, which is kind of a good thing because I'm kind of into that whole subject. And well, normally I would be spending the evening under the dome presenting a planetarium simulation or show in our brand new planetarium, which unfortunately we can't use right now because of, things, right? But that's okay because we get to do this instead, right? We get to have these conversations with a lot of really interesting people. And for those of you who ever, if you're new here, what I would love to ask is please let us know in the chat. Just say, hey, I'm new, or hello, and let's say hi to you and all that kind of stuff. Let me also ask you, have you ever looked through a telescope before? It might seem like a silly question. I know many of you are all amateur astronomers, and there's even some professionals in the audience, but have you actually sat and looked through a telescope? And give me a yes, give me a no, and let's see what you all think. So we got a few folks checking in here. We got a couple of my students coming in saying hi. Got Sophie Coleman. Hi, Professor. How you doing, Sophie? We got Tiffany. We've got let's see. Well, they're going in a little bit too fast. I got Charles Sidney here. So it's kind of nice to see some of my students. And I want to thank all my students for coming by and joining us this evening. Yes, I know you're getting extra participation credit, but you know what? That's okay. Sometimes it's good just to do it anyway and enjoy the show a little bit. So big welcome to some of my more friends, Frank Bowles. So I did ask, have you had a chance to look through a telescope yet? And I'm actually seeing a few yeses and nos, right? I'm seeing howdy and yes. I'm seeing yes. I'm seeing no, never actually. Yeah, it's interesting because a fun fact is that, believe it or not, many professional astronomers, as part of our everyday lives, as part of our work lives, our professional jobs, we don't actually look through telescopes. And that's not to say that's true of all astronomers. It's just that it's kind of a reality of the world that we live in today when you have things that are very remote. Telescopes are situated very, very far away. You can't actually use them like you would with a backyard telescope. You often have to use them via a remote interface, or even sometimes you just send a request and they think about your proposal, and if they decide to grant you time, someday you'll get an email saying, "Hey, your data is ready," and you download it and you start analyzing all that kind of stuff. But whether you look through a telescope or whether you use it remotely, the key thing is that the telescope remains the most fundamental instrument that we have for understanding the cosmos. It's our window, it's our eye into the universe. And we've been building them bigger and more advanced and more capable ever since Galileo first looked through his spyglass in 1609. And in astronomy is one area where bigger is actually better. I mean, having a bigger telescope means you can collect more light, which means you can do more science. So we've been building them bigger and bigger and bigger. But my guest tonight is working on a telescope that, when completed, depending on the timing, will be the largest telescope ever constructed, either on the Earth or even in space. And his name is Dr. James Fanson. He is the project manager of the Giant Magellan Telescope, who's a little bit out of focus here, which is kind of perfect considering as we're talking about telescopes, but we're going to go ahead and get him back into focus in just a moment. But I want to welcome Jim to the show. Jim, good evening, and how are you, sir?
Very nice to be with you, Chris. I'm pleased to be here.
Well, thank you so much for coming by and spending some time. Jim, I know that you are currently working on, as I said in my intro, the largest telescope that's ever been constructed, apart from the other. But we'll talk about that later. But I wanted to ask did I characterize the kind of like why you're building such a great big telescope? I mean, why do we need a great big telescope, and why is it called the Giant Magellan Telescope?
Well, let me take those in order. The fact is that most of the objects that we look at in the cosmos are very far away and they're very faint. And if you just look up at the sky with the naked eye, you can see about 6,000 stars, and the Andromeda Galaxy is about the farthest thing that you can see with the naked eye. But if you want to study objects deep in the universe, they're very faint indeed. And so the main purpose of the telescope is to gather light, uh, to gather more light than your eye can gather. And because of the nature of the physics of light, the larger the light collecting aperture, mirror or lens, whatever collects light for your telescope, the larger that is in diameter, the sharper the image is, the more resolution you can achieve. And so you can look at things in more detail. So to get an understanding of what's going on in the cosmos, to understand the chemistry, the physical processes going on, you need to gather a lot of light, and you need to look at things in as sharp a resolution as you can. And so that's what drives us to ever larger telescopes. In fact, the history of the telescope is really a history of how big of a light gathering mirror or lens can you build, and what will your budget afford.
I told, yeah. So you're obviously you're limited. You sound like a project manager to me, right? You're limited by your budget and the scope of the mission, so to speak. So, what then is the primary? What would you say? We're talking about the Giant Magellan Telescope. First of all, let's just address some fundamentals. What makes it giant? I mean, I know it's big, but how big are we talking here?
So this telescope will be 25 meters in diameter, the light collecting mirror. Today's largest telescope is about 10 meters, and what we discover if we look at the largest telescope in the world over time, going all the way back to Galileo, we find that the size of the largest telescope in the world doubles about every 30 years. So the technology advances to the point where you can double the size about every 30 years. So the current generation of 8 and 10 meter telescopes, which are the largest in the world today, were really built in the 1990s. So the time is ripe for the next doubling, and that's where we're at, about 25 meters.
So we're talking about a 25 meter telescope, but we talked about you talked about how you are bringing that light to a focus, and you mentioned mirrors earlier. I know that I know many of my audience here are familiar enough with telescopes to know that it's largely done with mirrors and not lenses anymore. It hasn't been for some time, but how is it that how do you get a 25 meter mirror? I mean, you don't just order one from the mirror shop, and you certainly can't. Can you build a mirror that's physically 25 meters across?
Well, you might be able to build a mirror that was 25 meters across, but you could never transport it anywhere down the freeway because
Oh,
it would just be
okay.
too hard. So what we do is we make use of a breakthrough that occurred in the 1990s with the Keck telescope that's on Mauna Kea, which is to segment the primary mirror into a number of separate mirrors and then phase those mirrors together to make them behave as though they're part of a single mirror surface. And we're talking about very high accuracy here. When you polish a telescope mirror, it needs to be polished to the correct shape to a small fraction of the wavelength of light. Typically, we're talking about a millionth of an inch. That's the level of accuracy you need. So if you're going to make a mirror out of segments, which is what they did on Keck and what we do, you need to manufacture those individual segments, and then you need to phase them so that they appear to be sort of cookie cutters out of a single optic.
Mhm.
So what's different about our approach to what was done with Keck or the other segmented telescopes is that we form our primary mirror out of 7 individual mirror segments, each of which is 8.4 meters in diameter. So each of these mirror segments is already the largest mirror made in the world.
Right. I was saying
Uh,
that's pretty colossal.
we're
Yeah.
making 7 of those, and we aggregate them basically to form our primary mirror.
So we have up here a diagram of kind of like the current state of the art and then what you're building. So you mentioned Keck earlier, which is a 10-meter mirror that's composed of, I think, 36 hexagonal segments. I'm representing here the 10.4 meter, slightly larger Grand Telescope in the Canary Islands. But you could just see the aperture comparison. You notice that we're drawing like a circle to kind of represent like the effective aperture, right? I mean, you've got some necessarily have some gaps there. Could I ask, why are you going with these 7 large mirrors and not just adding more hexagons? I know there are other telescopes that are under development that are taking that approach. What led GMT to choose this particular configuration?
So that's an interesting question. So the answer is that there are image quality advantages if you minimize the number of edges uh, in the segments that make up your primary mirror. When you make up a mirror of segments, and I talked about this phasing that you have to do, you can never get them perfectly in alignment and perfectly in phase. And every edge that you have, every gap that you have is a source of stray light. And so by using these very large monolithic mirrors, these 8.4 meter mirrors, we have beautiful, continuous, smooth mirror surfaces, and we have far fewer of the edges that cause stray light. And that's important when you want to do something like what we call high contrast imaging. If you're, for example, if you're trying to image an exoplanet that's orbiting a nearby star, the difference in brightness between the planet and the star can be 1,000,000 to 1,000,000,000 to 1. And so you're trying to image like an insect that's flying around a searchlight at night. And so you want to try to suppress the light from the star and pick up this very faint planet that's orbiting nearby. And that huge contrast means that you need to minimize the amount of scattered light, stray light that can contaminate that image. And we feel that this approach will give us some real advantages there.
So you're, let me see. Beg your pardon. I got an old chat from a previous stream up on my screen. My apologies for that. So we're taking a look at your slides right now. This is your doubly segmented optical design, and again, you're talking about 7 primary mirror segments. I understand that there's an 8th that will be cast. Is that correct, or is that still in the plan to serve as a spare?
Yeah, that's what we call it, an operational spare. You'll notice in this image that the
Oh, let
7
me go back to
segments
it.
involve 6 segments form an outer ring, and then there's a center segment with a hole in the center. That's where the light comes to a focus and where the scientific instruments are located. And so we have only 2 different optical prescriptions. The 6 outer segments are in an off-axis shape. You can think of taking a cookie cutter to a large 25-meter mirror and cutting these 8.4 meter segments out. The ones out at the edge are not axisymmetric. They have a bit of a potato chip shape. And so all of those 6 segments on the outer ring are identical. But the one in the center is different. That one is on axis. That one has an axisymmetric shape. So 2 optical prescriptions, which is also a simplification for us. If we had many hexagonal segments, we'd have many different optical prescriptions. But the idea here is that on a telescope, the light needs to reflect off the mirror, and so you need to coat the glass with a reflective coating. We're going to be using aluminum, usually aluminum or silver is what's used. And so the whole purpose of the glass mirror is to position these few atoms of metal that actually reflect the light. In our case, we use about a half an ounce of aluminum to coat each of the primary mirror segments. But those coatings degrade over time. They get dirty, there's some corrosion or oxidation that occurs. So periodically we need to remove the mirror segments one at a time, remove the old coating, put them in a coating chamber, and then put a fresh coating of aluminum on them. And that takes some time. So what we've planned to do is to have an 8th segment that's polished to the prescription of these outer 6 in the telescope. so that we can remove one of those 6 segments and then put this operational spare in there and continue science operations with a full complement of mirrors in the telescope. And then, in parallel, we'll go off and put a fresh coating on the mirror segment we removed. So it's an improvement in operational efficiency, if you will, to have an 8th segment. We don't actually need one, to operate the telescope, but it improves the efficiency.
So we had a question, and first of all, I see a few comments coming in and some very kind words. Thank you very much. And as always, I'm behind the scenes trying to make sure I can keep everything running and understand and not screw things up too badly, I hope. But I did see a question a moment ago, and I think, yeah, here it is. This is from, and I'm probably going to mess up your name, and I don't want to ruin it, but I'll just ask the question is, what kind of wavelength does Magellan excel at the most? It's an interesting question because it sounds like, you get different telescope mirrors or different telescopes are sensitive to different wavelengths of light. Where would you put GMT in terms of its optimum performance?
Well, GMT is designed to operate in the visible part of the spectrum and into the infrared. So for the short wavelength, then, we're talking about a third of a micron or so, and then we'll be going out into the near infrared. When you get too far into the infrared, you enter what we call the thermal infrared, and then you're looking at the radiation from heat. And because our telescope is on the ground, it's in the Earth's atmosphere, it's at ambient temperature. So at some point, the infrared background from the telescope itself becomes too much of a noise source. The other aspect of how we're going to do this is we incorporate what's called adaptive optics into the telescope design. We have a segmented secondary mirror, which consists of deformable mirrors that have about 6,000 actuators on all of them. And we use that system to correct for the distortion that's introduced by the Earth's atmosphere. And that correction will work best in probably around a micron or a little bit longer. So while the telescope will operate into a fairly short wavelength range, probably its best optical performance will occur around a micron or so. But we have our first light instrument, which is a very high resolution spectrograph, which is designed to find Earth-like planets orbiting other stars. Will operate in the visible part of the spectrum, and that's what we're going to go in the sky with first.
So okay, so it's interesting because I know that we're talking about adaptive optics as a way of overcoming the distortions due to the atmosphere. What I wanted to, and what's been pointed out, was that it's interesting, and it just is right here. This is Frank Kinney's comment. Interesting that GMT does adaptive correction on the secondary. So normally these adaptive optic systems are done post-primary mirror, or I should say post-secondary mirror. So the light reflects off of the primary mirrors that you see there. They reflect to the top of the telescope, which is the secondary, and then down through the donut hole. And then there's where the adaptive optics package comes into play that corrects for the distortions in the atmosphere. I was wondering if you happen to know what the rationale was or how it was chosen to situate the adaptive optics right at the top of the optical structure, so right at the top there at that secondary.
Yeah, that's right. That's a good and interesting question. So traditionally, adaptive optics on telescopes is implemented with what we call a post-focal arrangement. So the adaptive optics mirrors and whatever other mechanisms or optical elements are associated with it, usually there are several of them, are located after the telescope comes to focus. So the light will come into the telescope, reflect off the primary mirror, the secondary mirror, then probably off a tertiary mirror to bring the beam off the telescope into the adaptive optics bench, and then reflect off several other mirrors. The advantage of putting the deformable mirror up at the secondary is that we can now do the adaptive optics correction and deliver light to our scientific instruments after only 2 reflections. And this improves the efficiency of the telescope because the throughput, the optical throughput, the amount of light, the fraction of light that actually gets delivered to the science instrument is much higher because you lose a bit of light with every reflection.
Right.
So the more reflections you put the beam through, the more light you're going to lose. So it's not just that the telescope has to collect a lot of light, the telescope has to deliver a lot of light to the scientific instruments. But there's another advantage, and that is that if we do the correction at the secondary mirror, we're able to do a correction over a wide field of view. And our particular optical design, which is a Gregorian optical design, uh, gives us a very uh, wide field of view, about 20 arc minutes in diameter. And with the adaptive optics at the secondary, it's actually conjugate to about 160 meters above the primary mirror, which is where the ground layer turbulence tends to occur for air that's flowing over the surface of the Earth. Because that correction occurs relatively close to the ground, we can correct or significantly improve the optical quality over a wide field of view, which is something you really cannot do with a post-focal adaptive optics system. So there are a number of advantages in putting the adaptive mirrors up at the secondary. And we're not the first people to use
Oh, really?
this approach. So there's an adaptive secondary mirror on the Large Binocular Telescope that was built on Mount Graham in Arizona, and there's adaptive secondary mirrors now on the European Southern Observatory in Chile, and there's an adaptive secondary mirror at the Magellan Telescope at the same location in Chile where we will be building. So
Well, I
this
think
this is a proven approach, and it has some real advantages.
so. And so that's a pretty good segue into Bez's question. He's asking, where will the Giant Magellan Telescope be located, and how accessible will it be to professionals, and how can the general public enjoy it? So there's a couple of different layers to that question. Thank you for that question, Bez, because that's actually something I was going to ask, and you kind of beat me to it. But that's awesome. My question, if I might rearrange the question just a little bit, is you mentioned that it's being situated in the Atacama Desert in Chile. Why did you choose Chile and not, say, Towson University, where I work,
So
or my
the
backyard?
sighting of a telescope, that's a really interesting question. So you can't put a telescope just anywhere if you want to get good observations of the heavens. When you sight a telescope, you're looking for some characteristics. You're looking for a place that's very dark. You're looking for a place that has very low moisture in the air column that you observe through, because it's the water vapor, the moisture in the air that absorbs light and prevents light from certain wavelengths of getting through the atmosphere. And you want a location where the airflow is very steady, so that it doesn't cause the image to jump around. When you look up at the sky and you see a star twinkling, that's resulting from the airflow over you, where different cells of the atmosphere at different temperatures, different refractive index, it bends the light around as it comes through the atmosphere. You want a site that's got very smooth air. And it turns out that those locations on the Earth tend to be on the top of mid-Pacific or mid-oceanic, I should say, volcanic islands like the Hawaiian Islands or the Canary Islands, or continental coastal mountain ranges. And it turns out that the Chilean Andes are about the best quality location for these various qualities I mentioned. The highest quality seeing you can get very dark skies and very low moisture. And soon, the majority of the telescopes that are doing scientific work are going to be located in Chile. It's just an area where a large number of telescopes are being built. So that's the reason that we would like to be in Chile rather than in the middle of the continent.
Okay.
But the consortium that's building the Giant Magellan Telescope consists of about a dozen scientific institutions. One of them is the Carnegie Institution for Science, and they have a large piece of land in Chile where they chose to build their observatory several decades ago. In fact, they built two 6.5 meter telescopes that they named the Magellan telescopes, I think after the Magellanic Clouds, which are small dwarf galaxy companions of the Milky Way you can see in the southern hemisphere. And because we're building it at their site, they're hosting us basically on their land. They reserve the highest peak for a future telescope, and that's where we're putting the Giant Magellan Telescope. And because we're bigger than the Magellan telescopes that exist down there today, we are the Giant Magellan Telescope.
Okay, so if I understand it correctly, so what you are saying is that in addition to the fact that Towson University is not one of the contributing institutions to the GMT project, you would have considered Towson as a suitable location if it weren't for the fact that it was one of the worst possible places in the world to actually build such a precision telescope. So it wasn't personal. Okay, that's what I needed to know. but no, that's
definitely not. It's definitely not. Nothing personal there.
Okay, great. Well, and I hope my wife is watching because she thought, Anyway, no, but seriously, in all seriousness, this is why you have to. I mean, you're not building it where you work either, right? I mean, you have to situate these at these very remote locations that just happen to be, well, more or less perfect. At least one of the best places on Earth. They also happen to be pretty inaccessible as well. And I also just want to quickly say thank you very kindly to none other than the Emperor of all mankind. So thank you very much for coming in tonight. I blog content creators. I'd like to thank Dr. Fanson for giving his time. Small as we may in numbers watching, appreciation is huge. Long live me. Yes, thank you so much, Emperor. We appreciate you as well. And seriously, thank you, Dr. Fanson. This is really cool. Oh yeah, my wife's also right. The county planning commission wouldn't allow it. Yeah, she checked. So now we know why we're situating it all the way down in Chile. I mean, I know that there's locations in the northern hemisphere. This will give you an unprecedented view of the southern hemisphere of the celestial sky. I was wondering, and I wanted to ask, you mentioned, part of that question that we had a moment ago was what kinds of science would be done with it. And what I wanted to ask you guys watching is if you can let us know in the chat, if you were granted time on the Giant Magellan Telescope, and maybe you were granted like an evening's worth of observations, what would you use it for? What? And please don't say spying on your neighbors. Okay, we're not going to allow that. But what astronomical purpose would you like to use it for? If you could just use it for anything, what would you look for? What would you look at with it? Let us know in the comments. All right, please put a chat in there. Tell us, and that'll help us to think a little bit about the kinds of science we're going to be doing with GMT. Not that Dr. Fanson's worried about it. He's got a bunch of astronomers already lined up to use this telescope. But hey, I thought I could ask you what you would like to see with it. In fact, to that end, I think there were a couple of people asking, let's see. Actually, this is a bit relevant to this day and age that we live in because we're now seeing yet more and more and more of these Starlink satellites that are going up. And I know that there's a commission from the American Astronomical Society to figure out how to mitigate how we're going to deal with this. What's your understanding of the GMT mitigation plan for Starlink?
Yeah, this is an interesting and timely question.
I guess we should clarify for everyone watching. I didn't mean to interrupt you, but Starlink is a constellation, a mega constellation of very low-flying satellites to give us broadband internet from everywhere. Yay! But it also kind of photobombs all of our telescopes, which is not so good. So back to you. I wanted to ask what you thought, Jim, about the plan.
Yeah, so I think this took some of us a little bit by surprise to discover that there were actually plans to put thousands or tens of thousands of satellites in Earth orbit. I mentioned earlier, when you look at the night sky with the naked eye, you can see about 6,000 stars. So we're talking about putting more satellites up there than the number of stars you can see with the naked eye. And it is a concern. And not only the American Astronomical Society, but the International Astronomical Union are looking at what the impact can be and how to mitigate this. And for the Giant Magellan Telescope, I think that the impacts are less significant because we can choose which area of the sky to look at. You can imagine if you know what the orbits of these satellites are, and you know what time you're going to make an observation, you could time those observations to avoid interference with a passing satellite. We also have a relatively small field of view. We're trying to magnify objects and get high resolution images, and so the actual amount of the sky that we look at any given time is quite small. I think the impacts are more severe for telescopes such as the Rubin Observatory that is doing a large survey of the sky. They survey the entire sky every few days. And so they will inevitably be capturing a lot of these satellite trails in their imagery. And they're working right now on data processing techniques to flag which parts of the image are affected by a satellite, or to correct the impact on the images. And I should also say that the satellite manufacturers, they're also astronomy people. They're sort of geeks like we all are, and they don't want to make it difficult to do astronomy from the ground. So they're actively working to mitigate the impact by, for example, making the satellite surfaces dark and low reflective, so that the amount of light that they reflect is minimized. So we're going to have to learn how best to mitigate the impact, but it is an area that we're actively looking at, and some of us are actively working on.
Sure. And while we were talking, I just want to say thank you very kindly to, let's see, well, we had a super chat earlier from Paf Medic, Jan, who is, are you down in Australia, Paf? I don't know, but I thank you both very much for a wonderful show. Thank you very much for supporting the show. Really do appreciate this so much. And by the way, we will try to make sure that super chats, if you have a question attached, that we will answer those in priority. If you're a student of mine, just simply say student and don't super chat because you're broke, and that's not allowed. But if you aren't a student, then we'll try to put the super chats in priority. But seriously, I want to get to all the questions that we possibly can, because I did ask a moment ago about what people would like to use the GMT for, and we had a few cool things. I mean, hey, who says, hey, I like to look at the moon? Oh, that would be kind of cool, wouldn't you think, to look at the moon? I think we'd be able to see some very fine detail, well, relatively fine detail on the moon, correct?
Absolutely, you would be able to see detail on the moon, but you will not be able to see the Apollo landing
Right.
module. The telescope's not big enough for that.
Right, and even the extremely large telescope won't be big enough for that. You need, I think you would need something in the 200-meter class range. I could be wrong, but it would have to be a very, very big telescope. Bram says, pointed at Earth to search for intelligent life. Good luck with that. Chikali says, faraway planets. Well, that's actually pretty relevant. I mean, I know that there's a lot of exoplanet research that's already being queued up for GMT. Is that correct?
Yeah, that's right. This is an area of really deep and broad interest. We want to know in this journey we're taking through the universe, if we're traveling alone, or whether there's other life out there. And the first light instrument, that is the first instrument we're going to go on the sky with, as I mentioned, is designed specifically to search for and characterize Earth-sized planets, as rocky planets that are orbiting around nearby stars. So that's that's definitely an emphasis that we plan for GMT. And we can search for and characterize planets in a couple of different ways. Probably the most common way that exoplanets are detected from the ground is by what's called the radial velocity method, where you're actually measuring the Doppler shift of the light coming from the star that is Doppler shifted because of the gravitational tug of the planet that's orbiting. And so you can imagine that the star doesn't move very fast as the planet goes around it. Typically, is moving on the order of in the meters per second range. And the lower the mass of the planet and the farther away it is from the star, the lower that amplitude of motion and that velocity becomes. So it's a challenging measurement when you're talking about planets that are small. And our first light instrument is going to provide the most sensitive radial velocity detection ever put on a telescope. And that will open up a whole, a huge detection space for us to find smaller planets.
And
Once we locate.
So to be clear, you're talking, when you say radial velocity, you're talking about you're taking the spectra of a star, and if there's a planet going around it, it's going to exert a slight gravitational pull on the star as they go around the system's center of mass. And that star is going to appear to come toward and move away from us, and there's going to be a slight Doppler shift in the spectra back and forth, right? So this is what reveals.
That's exactly right.
All right, so that's what reveals the planet. That betrays the presence of the planet. It reveals the spectra of the star, of course. So you're saying that these would be the highest resolution spectra ever achieved?
Well, we have a very high resolution spectrograph, but our ability to detect the radial velocity shift would have unprecedented sensitivity. So we're talking about well below 1 meter per second. So you'd be detecting the change in velocity of the star along your line of sight back and forth, at a rate which is very very slow stroll down the sidewalk. That's the kind of speed we're talking about. Then once you are able to determine that you're looking at a rocky planet, then what you want to do is characterize the atmosphere of that planet and see if there are any signatures of oxygen or ozone or carbon dioxide or methane and so on in concentrations and relative abundances that would suggest that there are life processes on the planet. So that's another area where we are going to be focusing on exoplanets. So one method is to look at the spectra of the star when there's no planet passing in front of it. Occasionally the orbital plane of a planet around another star will line up so that the planet will actually pass in front of the star along your line of sight. And when the planet is passing in front of the star, now you're measuring the spectrum of the star as modified coming through the planet's atmosphere. And when you take the difference of the two, you can attribute what the spectral signature is coming from the exoplanet. So by having such a large telescope, we're going to have a lot of light that we can spread out into a spectrum and get exquisite spectral resolution and get the kind of detailed measurements to determine these specific molecular constituents in the atmosphere. And that's very exciting because ultimately we'd like there to be a Star Trek in our future. We'd like to have places to go. We want to find the M-class planets, as they say.
There you go, the M-class planets. Excellent. And I think this directly speaks to Martin's question about will it show exoplanet atmosphere composition, and the answer is yes, under the right circumstances.
Absolutely.
Yeah, absolutely great.
Yeah, absolutely.
Chakili says science. Yes, that's exactly right. I think there was a couple of other questions about this. The NASA dude asked, could it be used to image black holes directly, at least in the Milky Way?
So I think the answer there is that we don't have a large enough aperture telescope to take an image like you saw that came from the Event Horizon Telescope that essentially synthesized radio telescopes across the whole Earth. But what we can do is we can characterize the emission of material that is close to the black hole, and characterize what's going on in these very high gravity environments around black holes and learn more about them. And that's where the spatial resolution of a larger telescope becomes important. It's also important if you want, going back to the exoplanet discussion, if you want to actually separate the light from a planet from the star it's orbiting and bring back a family portrait so you can see the star orbiting, you need that kind of resolution. And we know, for example, that there's a rocky planet that's orbiting Proxima Centauri, the closest star to our solar system, and it's visible from the southern hemisphere. And with a telescope the size of GMT, we'll actually be able to image the planet orbiting Proxima Centauri b.
That'd be cool, yeah, to catch Proxima Centauri b and start characterizing it, and if it has an atmosphere, characterize that too. Hiroshi loves you with a €5 super chat. Thank you so much, Hiroshi loves you. We love you too. And could we take a photo of Eris with this telescope? I'd say yes. However,
I'd say yes. I'd say we're going to excel in doing images of faint objects, and we will have the ability to measure or take images, spectra of objects that are moving, relative to the stars up to a certain speed. We can make those images. Now, I'm not familiar enough about Eris to know how bright Eris would be at a given wavelength, but I'd say we will have the ability to measure objects that are even deep in the solar system.
Yeah, I would agree with Dennis. I think we're probably wouldn't necessarily resolve the disk of Eris, as cool as that would be. Maybe a pixel down to the pixel level, but that might be it. But what it sounds like this can do would be to get us the high resolution spectra of Eris and let us really properly characterize what it's made of, its temperature, its how much it reflects, its albedo, that kind of stuff. And I think that would definitely give us easily the most comprehensive look at Eris, short of a flyby mission. I mean, that's really what I think it would take. Actually, Johnny Cheese was asking, would GMT be used for the search for the Planet 9? Your thoughts on that?
I don't know that we have a white paper on Planet 9 or any investigators planning to do that kind of search. I think that, probably Planet 9 is a search is better suited for a specific survey mission that would be looking for, do comparative images and look for objects that are out there that haven't been detected yet. But I'm not going to rule anything out, because when you've got a telescope powerful of GMT, you can still do survey type of science programs. You have to be willing to spend the observing time to cover significant areas. But if you have some idea of where you might look for Planet 9 from other data, certainly you could do some deep kind of imaging.
It would actually have so it's going to have a reasonably wide field of view, right? So if you had a wide field instrument on it, in theory,
we'll have a well-corrected field of view out to 20 arc minutes. But the idea there is that we're really interested in taking spectra of objects.
Right.
So we have a large, what we call a corrector plate, where we'll have fiber positioners that can actually self-mobilize, move around to specific parts of the field of view. Mm-hmm. And then they're fiber coupled into the spectrograph. So if we want to make measurements of a large number of galaxies at the same time in a galaxy cluster or a star cluster or something, we can take that data simultaneously by fiber coupling a large field of view. So we do not have a camera that's designed to take an image across a 20 arc minute field of view.
Right.
But but we would like to be able to take advantage of the large field of view for doing spectroscopy.
Certainly, if not find it. If I think the Vera Rubin telescope, it's an 8.4 meter telescope, which not for nothing is also extremely big when you think about it as a single mirror telescope. That's going to have the wide field of view, and it's going to have the rapid, repeated imaging, so it's going to catch anything moving or going boom in the night. And that would include Planet
That's right.
9 if it's out there. It should be bright enough to be picked up by Vera Rubin. I would say that if someone does pick out a candidate Planet 9 in the data from Rubin, I think GMT would be a great follow-up instrument to really get a good look at it and verify it is what they think it is. Gumundur put in, you telescope-making scientists are just making mankind's mind expand and making us understand the cosmos we live in. Thank you. Well, thank you, and thank you, Jim. This is really cool stuff. And actually, to that end, I just want to throw some more. We have a huge we have a Jim Fanson fan here. Jim worked at many famous ground-based and space-based telescopes in the early 80s. At my home astronomy club, he built a massive 26-inch scope that we used for years, Milwaukee Astronomical Society. Jim, do you have any recollection of that whatsoever?
Yes, so what Frank is referring to, the astronomy club in Milwaukee, the Milwaukee Astronomical Society. So I grew up there, was a member of that club for many years. It was close enough to bicycle to from the home that I grew up in when I was a kid. And we had a large mirror blank that could be polished into a 26-inch aperture telescope mirror, and so we decided let's actually build this telescope. And so I designed part of the telescope structure for that telescope, and I helped lay the concrete block. Actually, there was the professional masons laying the block. We were just mixing the mortar and carrying the block up to them. So that was a great time. And in fact, that's where astronomy really took hold of me as a kid. I went out to one of the club open houses for the public and got a chance to look through their 12-inch telescopes, and it was just mesmerizing to look at Saturn and Jupiter and its moons, and look at the nebulae through these telescopes. And astronomy became a lifelong passion for me at that point.
Yeah, it's easy to get hooked on it, and I definitely had similar experiences. Although I never actually successfully built a telescope, I attempted a couple of times. But actually, speaking of building telescopes, since you are in the middle of building this one right now, I wonder if we could just quickly circle back a little bit to the actual construction fabrication. Do you? I understand you have. Is there I understand there's been some update lately in the development of GMT, and I was wondering if you could tell us a little bit about that.
Yeah, that's right. So we talked about these large 8.4-meter mirror segments that our primary mirror is composed of. And there are 7 of them. We talked about the 8th operational spare. So we've completed 2 of these mirror segments, and they're in storage now, awaiting transport to Chile. 2 others are in various stages of grinding and polishing. I should say 3 others are in various stages of grinding and polishing. And the 6th mirror we just cast about 2 weeks ago. And this process of casting these large mirrors is just fascinating. The technology was developed by Roger Angel at the University of Arizona. And for many decades, the largest mirror that anyone had been able successfully to manufacture and polish was the 200-inch mirror for the telescope at Palomar. And that was cast, and they were polishing that in the 1930s, and sort of got interrupted by the Second World War, and then they finished it shortly thereafter. And there wasn't a larger telescope than that worked until the Keck telescope was built in the 90s using this segmented approach with hexagonal segments. But recognizing the advantage of having smooth, continuous, large mirror surface, Roger and company and others were working on how to break through this 5-meter limit that had been achieved with Palomar. And he came upon this method of building a spinning furnace that has a mold made out of refractory material to sort of lightweight the mirror. You don't want a single solid blank of glass; would be far too heavy and flexible. So you want a lightweight, stiff mirror. So they developed this technology, and now there's basically a factory underneath the football stadium at the University of Arizona campus, and they churn out these huge mirrors, and they've gotten extremely good at it.
Hmm.
And we just cast mirror segment number 6. The furnace is still spinning. By the way, the spinning furnace causes a parabolic surface to form, just from the centrifugal force
I
on the
should maybe back us up just a little bit. I have up on the screen. I don't know if you can see it, Jim, but I have a video playing, and I apologize for not running this earlier. But this gives you an idea, number one, of the size of just one mirror. This is just one of the 7 mirrors. And what are they doing here, Jim? They're laying in these chunks of glass. Is that right? I mean,
Yeah,
this is just.
that's right. So the glass that we use is a what's called a borosilicate glass. It's a low expansion material. It's kind of like Pyrex.
Hmm.
And it's manufactured in Japan in very small batches in clay pots. And they break the mirror, or they break the glass up into like hand-sized pieces you can hold in your hand, and they ship that in cartons to the mirror lab. This is the Richard F. Karras lab at the University of Arizona. And then when the mold is machined, and the mold, each piece of this mold is machined individually. They're all slightly different, these hexagonal pieces. Um, then the technicians place 20 tons of glass on top of the mold by hand, and that's what you're seeing here in this video. And when the glass is all distributed across the mold, then the lid on the furnace is lowered, the temperature is raised, and the furnace is spun. And you can see from this time lapse from a camera inside the furnace, you can see as the temperature increases, these glass chunks melt and meld together, and they have the consistency of honey, and it flows very slowly in between these hexagonal mold
So this
uh,
is while the
pieces.
oven is spinning, right? This is while
Yeah,
the
so
spinning's taking
this time
place.
lapse is while the furnace is spinning.
Hmm. And so, and actually, Arduino has a important question, and let's see, we have here. I believe this is a time lapse video of this is after the spinning's been done. First of all, how long does it take just to spin in the oven like that? Like, that's not something you can just do in a few days or anything like that, right?
What we call the high fire period, bringing the furnace up to the melting point of the glass, and then cooling it down, that takes a few days to do that part of the process. But we want the glass to have very low stresses in it when it's cooled down to room temperature. And that's called the annealing process when you're cooling the mirror off. And so we cool the mirror very, very gradually. So as the atoms arrange themselves and lock themselves into position, but it does that with very, very little residual stress. So it actually takes several months before the temperature of the glass is back down to room temperature. So it's going to be, it's going to be several months from now before mirror segment number 6 is ready to be removed from the mold.
And then it's going to undergo some polishing, right? So here we're taking a look and we're seeing the completed cast. I believe this is what you call it, right? This is the cast coming out of the mold. And am I correct? Is this the
That's right. So
casting phase, or is this
yeah,
the end of
so
the casting phase?
this is the end of the casting phase where we lift the mirror,
Yeah.
including all of the refractory material, all of this lightweighting material, which then has to all be cleaned out with high pressure water jet by
Hmm.
hand by technicians, clean all of that refractory material out. So all that's left is the glass, and where the refractory material was are now these lightweighting pockets inside the glass blank. So that's what we do. We do a turning maneuver so that we can reveal the bottom of the casting, and that's where all the that's you're seeing now all the refractory material that
Okay.
has to be removed. Then we polish the back surface and we attach what we call load spreaders. We bond them onto the glass surface, and that's where the actuators are placed that support the mirror. The mirror sort of rests on a bed of nails. They're like 165 uh, pneumatic actuators that, uh, excuse me a second.
Sure, no problem. And as I'm playing producer back here, I'm trying to keep the video running, and I don't have the video of the polishing. I'm sorry, I don't have that one ready right now. I don't know if you have it in your slides at all, or if you have a photo of it. I could probably bring up a photo of it. But you're going to spend. I understand you're going to spend some time just polishing the glass, and that's going to take a couple of years. Is that right? Just to polish it?
That's right. It takes about 4 years from beginning to end
Okay.
to produce one of these mirror segments.
If you need to clear your throat, go right ahead. I can switch
I think
over
I have
here.
a frog in my throat here. Let me.
All right, no problem. So while he's go ahead and clearing out the throat, we'll give him a chance to clear up. And I totally understand what that's like, and I've had that happen to me too. It's never fun, but that's cool. And I also realize we're just about out of time here. So I think what we'll do is we'll take Jim, if it's okay with you. I think we'll take just a couple of quick questions, almost like in rapid fire succession. I don't want to rush you out, but I don't want to hold you up all night either. That's all. So.
No worries. I can stay as late as you like. And I've got more images of what the polishing and
Well, if you'd like to
and
extend, we can
process
extend.
is like.
We can hang out for a little bit longer, especially if you got some more slides to show. So why not? Sure. Okay. So you're describing the polishing process, right? That alone takes about 4 years.
It's 4 years from the beginning of the ending, including the casting,
Hmm.
the rough grinding, and the fine polishing and testing. So it takes about 6 months or so to grind and polish the back surface, and then it takes about a year to polish the front surface. And it's the polishing, of course, is a subtractive process. So you need to be very careful as you're removing material as you're getting close to the final surface, because if you remove too much, you can't add any back in. So then you have to polish the whole rest of the surface down. So this is done in an iterative process. And we're currently polishing the front surface of segment 3,
Hmm.
and it's down below about 90 nanometers RMS, and the final figure needs to be about 20 nanometers RMS. That's about the millionth of an inch level I mentioned earlier. This image you're showing is what the mirror casting looks like just as we've opened the furnace. And the technicians gingerly walk out and do an inspection and see if there's any defects or bubbles or anything that need to be polished out. And then moving to the next slide, this is what the back surface of a mirror looks like after we've cleaned out all the refractory material. You can see all of these holes in the back. Each one of those is one of the lightweighting pockets that was formed by these hexagonal refractory elements in the mold. And these are the load spreaders that I mentioned, which the mirror rests on, these 165 actuators or so. And we control the force in each of these actuators so that we can assure that the mirror is actually in the correct shape. So this is called an active optics technologies. We actually are constantly monitoring using reflected starlight through the telescope. We're monitoring the figure of the primary mirrors and correcting them by making minute adjustments on these 165 actuators. And now here is a picture of the front surface of the mirror being
Ah,
polished.
okay. So
So here you can see
it's turned right back up. It's turned back up right after
yeah,
everything's removed.
that's
Okay,
right.
I see.
That's right. So it's now resting on these load spreader supports on the back surface in what we call a polishing cell. And then you can see the white material is the grinding compound, and the mirror is slowly rotated. And then you can see at the upper surface, this is the polishing lap. And in this case, there are different laps that are used, but in this case, it's an active lap. So the lap has a series of actuators on it, and as it moves in an orbital pattern,
Oh,
the
so
computer
the lap is that
applies the forces.
circular. The lap is that circular device at the top of the image. The right?
That's correct.
Okay, so that's
It's
spinning.
the circular part with that. So that is moving as well in an orbital pattern, and the red, white, and blue cylinders you can see on it are actuators that deflect the shape of the polishing lamp, so that we can polish this large mirror into the off-axis shape that we need.
Wow. Okay. Actually, before we get to the off-axis part, we have a super chat here from Cheng Sai. Thank you so much for the $5 super chat. Really do appreciate that, Cheng. And it says, "Is the mirrored surface on the top? If so, why do both sides need to be polished? The top and the bottom." I think is what he's asking.
Yeah. So the reflective surface is on the top. That will have a very precise shape that reflects and focuses the light from celestial objects. We polish the back surface for a couple of reasons. The first reason is that we want to make sure that there are no areas where cracks can form and propagate that could create a catastrophic failure on the glass. So we want a polished surface for that reason. But we also want a very flat surface because we're going to bond on these load spreaders and actuators, and we want that done in a way that minimizes the amount of misalignment between those various actuators. So we don't polish the back surface to the kind of accuracy that we do on the front surface, but we do like to have a polished surface to work to.
Okay, so you're only polishing just that one side, but that's still going to take a few years. So you were describing that orbital lap, so that's going on. One thing I noticed, by the way, on that image, is you can actually start to see, if you look at it closely, there's a little bit of like concave curvature already there in the mirror, right? Like, it almost looks like it's starting to slope down a little bit toward the center, and that's as much a byproduct of just the casting process, because you're spin casting and you're letting centrifugal forces create a natural concave appearance, right?
So that saves us a huge amount of time in grinding and polishing, because the parabolic surface is much closer to the depth figure that we want to polish into the mirror, than it would be if it were just flat.
Mm-hmm.
So the mirror comes out of the casting process, out of the mold with a deeply curved front surface, and then we grind that with ever finer grinding compound. There's a specific machine that we use for the grinding, and then we move to the polishing machine to bring it to final specification.
So earlier, someone was asking about taking out the residual matter, and you have a honeycomb, so you get kind of like a lighter weight mirror. And then I think someone also asked, well, why then are you even using glass? And I think Amy here may have already preemptively answered the question. She says low COE, which I'm assuming you mean low coefficient of expansion, much more forgiving to heat fluctuation. Jim, does Amy get the gold star today?
That's right. Amy gets the gold star. So, I'm gonna channel Roger Angel here, who invented this mirror technology. It was Isaac Newton that really gave us the answer to use glass. Glass is a very stable material. It's an inert material. It doesn't react with the elements. And once you polish the mirror into a precise shape, you can come back 100 years later and the mirror is going to be in that shape, or it's going to be broken. One of those two options.
Oh, okay. So it doesn't bend or sag like cardboard. I mean, not cardboard. You know what I mean? Like even metal would fatigue after a while, but glass holds itself up pretty well.
So long as the stresses in the glass are kept below a certain threshold, glass is a very durable material. So I don't mean to suggest that the glass mirrors don't bend. They do bend. That's why we control them with the actuators on the back. But you will always be able then to bring the shape of the mirror to the same shape as what you polished. So that the glass is not going to flow over time, for example. It's going to retain the shape that you polished into it.
Fantastic. So we're seeing some huge praise for Amy. And actually, Martine is asking, how much do the actuators for the adaptive optics warp the mirror? Okay, so now we're coming off the primary. We're going up to that secondary tree of seven reflecting mirrors, and you have actuators behind them, pivoting and pushing in the mirrors in and out. Can you describe that a little bit in more detail? How much do they, or maybe how often do, like, what's the frequency? Do you know? And I don't know if you have a
So,
slide on that or you like to show, but I can.
so I don't really have a slide on that. So when
Okay.
we polish the mirrors, the mirrors are sitting on these load spreader attach points in what we call a polishing cell, and we adjust the amount of force that is uh, at the different attach points into a prescribed load condition. And then we polish the glass to very precise shape, to a millionth of an inch or so. And then we place the glass into a mirror cell that will ultimately go onto the telescope. And that's the mirror cell where we now have these uh, pneumatic actuators that we control the force that they exert. So the idea is that we bring the force uh, uh, on the various attach points to the same level that was applied when it was being polished in the polishing cell. And in principle, then that should bring the mirror to the exact shape that we polished it in. Now, as the mirror temperature changes, its shape will change slightly as we put the telescope in a different orientation, look at a different part of the sky from from zenith. The gravity will cause the mirror to distort slightly. So the forces we then
Hmm.
apply to the back of the mirror are to keep it into the precise shape we polished it when it was in the polishing cell. So, we're talking about very, very small deflections of the glass. You're
Hmm.
down at the wavelength of light. So we don't need a lot of deflection, but if the telescope is going to form what we call a diffraction limited image,
Hmm.
the best resolution that the physics would allow, then the surface has to be accurate, to like a quarter of a wavelength of light or better. And so we apply these forces on the back and achieve very small deflections in order to keep the mirror surface at the precise surface shape that we need.
So if you had a really good working mirror with a stable atmosphere and adaptive optics, how would that compare to something like the Hubble Space Telescope? I mean, that's sort of like the telescope, right? And it gives us these incredibly high resolution images, but it's only a 2.4-meter mirror, and so
Yeah, that's right. I
right.
actually have a figure on that. Let's see if I
Yeah,
can bring this
sure,
this
go right ahead.
figure up for you. So if this is the looking down on our telescope, these are the 7 mirror segments, and each of them is 8.4 meters in diameter. The size of the hole in our center segment is the size of the mirror
Wow.
in the Hubble Space Telescope. So
Wow.
the Hubble telescope is 2.4 meters in diameter. So our telescope is 10 times the aperture of Hubble, and therefore, with the aid of adaptive optics to correct the atmosphere, we'll be able to form images that are 10 times sharper than you can get from the Hubble's
Hmm.
telescope, just because the telescope is larger. And then later this year, NASA is planning to launch the James Webb Space Telescope, which is a 6.5 meter telescope. So this shows the comparison. The
Sorry,
Webb,
I shouldn't laugh. I mean, we're constrained by this, by the launch vehicle and all that kind of stuff. But holy mackerel! Okay, please continue. I'm
right?
sorry.
So what this shows you is that two things. First of all, the James Webb is going to be a much larger telescope than
Oh,
Hubble.
sure.
You
Yeah.
know, and we've all been mesmerized by the images from the Hubble telescope. James Webb will do much better resolution than Hubble. But what it also shows you is that a ground-based telescope like the Giant Magellan Telescope can collect much more light than you can from a space-based telescope.
Hmm.
So it's actually an interesting complementarity between telescopes in space and telescopes on the ground. They each have their strengths, but one of the strengths of telescopes on the ground, like the GMT, is our ability to collect huge amounts of light so we
Right.
can take spectra of faint objects that you would never be able to do from space. And in principle, we can achieve these very high resolution images, if we are prepared to use adaptive optics.
So, what would the images look like? I mean, I know you don't have an image from the future, but Like if we were to compare that to say Hubble and James Webb, what would you expect or anticipate it looking like? Can you describe that?
Yeah, so I have some comparisons here.
Ah,
So
okay.
this is
Looks like I asked the right question
this
then.
so if this is an image, of a small part of the sky looking at stars. This is in the near infrared part of the spectrum.
Oops, I'm sorry, I'm
Um,
getting my slides mixed up here. My apologies. There you go. Go ahead, Jim.
no worries. So this shows you what a collection of stars in the sky would look like under high magnification, but limited by the Earth's atmosphere. This is the turbulent nature of the atmosphere I mentioned earlier that causes stars to twinkle when you look at them with the naked eye. And it does not matter how large your telescope is on the ground. The resolution you're going to be able to image, the sharpness of the image is going to be limited by the atmosphere. I'm showing here some about 6/10 of an arc second resolution,
Hmm.
and and that's because the atmosphere is distorting the wavefront of light that's coming through the atmosphere. Now, if you get above the atmosphere, like telescopes in space, um, then let me take you to the next frame. This is a picture from the Hubble Space Telescope from,
Hmm.
I believe this is from the near infrared camera.
Hmm. So that's an
And
actual
you can see
picture.
how much
Okay.
sharper.
Yeah.
This is an actual image. This gives you an idea of how much sharper you can achieve, even with a small telescope, but getting above the Earth's atmosphere. And then if we go to the next frame, this shows you a comparable field from the James Webb Space Telescope, larger yet at 6.5 meters. And then for a 25-meter telescope, the diffraction image would look like this. So this is
Wow.
what we're striving for with the GMT. Now, we won't quite achieve this kind of performance because this doesn't account for this 7 individual segments in the pupil of our telescope and so on. But essentially, we'll be able to achieve diffraction limited performance in near infrared uh, to be able to probe the heavens with that much more uh, resolution and sensitivity.
I think people are appreciating the capability, and I think that that alone can sell just about any skeptic on why you'd want to build it uh, on the ground. Now, obviously, there's maybe one and very important caveat here, and that is we're considering a certain band of the infrared, right? We're not comparing optical or visible light to visible light, which, as I understand, and you can correct me if I'm wrong, but my understanding is that's largely a function of the technology of adaptive optics. Like the adaptive optics technology that we do have works well for the infrared part of the spectrum because the wavelengths are longer, so we can make those kinds of adjustments. We haven't gotten good at doing visible wavelengths, which are much shorter wavelengths, and getting those fine tuned. Is that correct? Is that a reasonable
Yeah,
characterization?
it's more difficult to do adaptive optics correction at shorter wavelengths,
Yeah.
and that isn't to say that the technology will not continue to improve over time. And the adaptive optics will provide improvements in image quality at shorter wavelengths. But if you want to achieve the so-called diffraction limit, if you want to get to where you're actually looking at the interference uh, uh, pattern of a point source, then the adaptive optics really excels in the near infrared part of the spectrum. So by the time we get out, to where we're showing these simulations, we'll be able to achieve very high, what's called Strel ratio, very high diffraction limited performance.
Cool. And Cheng asked about how does fast does it? I think you spoke to that earlier. Could you maybe repeat what the expected frequency is? Like these are going to be constantly analyzing the sky and constantly making adjustments. Do you kind of know what the frequency of that would be?
Yes, I do. And let me move to another graphic here.
Sure.
Um, this graphic shows the secondary mirror of our telescope, which is also segmented. So there's 7 1 meter diameter mirrors, and these are the adaptive mirrors. And you can see an example of what they look like in the left-hand image. They're about 600 72 actuators that are controlling a very thin, what we call a face sheet. So the actual reflective surface of what we call the adaptive secondary mirror is a 2 millimeter thick sheet of zero Dürer, or low expansion glass. So it's a meter in diameter and 2 millimeters thick. So it's very thin and very flexible. And we bond onto that thin face sheet a number of magnetic features. And then facing that is a reference surface that has electromagnetic actuators. And so when there's no electricity flowing into the mirror, the 2 millimeter thick face sheet is just securely against these electromagnetic actuators. But when we want to energize the mirror, we actually push the face sheet off the actuators and it floats in a magnetic field. And then we can control the shape of this thin face sheet with all of these actuators across all the segments. We have some 6,000 some actuators, and we update the position of that thin face sheet about 2,000 times a second. And that's the kind of bandwidth you need if you want to really correct the distortion from the atmosphere, because the atmosphere is turbulent and these cells of different temperature are flowing over your telescope, creating very high frequency content in the what's called the seeing, or the turbulence in the image.
I think I think this chat comes in just the right time. That sounds like sci-fi, but it works. It is it's something that we are building, and actually we have working examples of this. I mean, adaptive optic systems are used in other telescopes. Although this is to date the largest, by mirror size, adaptive optic system yet developed. So there was I think Ardwayne asked what things are of interest in the near infrared versus visible. If that hasn't already been covered, Jim, did you want to take a shot at that, or I could take a shot at that? How would you like?
Oh, sure. So, what you have to bear in mind is that when you're trying to understand a phenomenon that's going on in a celestial object, you're generally trying to understand, what is the chemical composition, what are the chemical processes that are going on, what are the physical processes, what's the temperature, the pressure, and so on. And the way you are able to determine that information is by taking the spectrum of the object that you're looking at. And often you want to take the spectrum of very specific locations and then move to the next location, take a spectrum. And the spectrum has meaningful information basically across the entire electromagnetic spectrum. So, if you're looking at very high energy processes, like a supernova collision or something, it's emitting neutrinos, it's emitting gamma rays, it's emitting X-rays, it's in the visible and the infrared output to the radio. So to really understand these processes, you often need to take data in as many wavelength ranges as possible. So, you can see, if you're probing in the atmosphere of an exoplanet, for example, there are certain chemical fingerprints that will show up in the visible part of the spectrum. There are others that are going to show up in the infrared part of the spectrum, and you really want to take that all in order to get as complete a picture of what's going on in that process as possible.
I would also say that when you're trying to look at very distant objects in the distant universe, they're going to be redshifted. That's because the universe is expanding and it's literally carrying the most distant galaxies away from us faster. So the farther away they are, the faster they're moving. And what that does is that actually redshifts their spectrum. In other words, all of their spectral information gets shifted into the red and even into the infrared part of the spectrum. So if you want to see what a galaxy is doing and what it looks like and what's happening in a galaxy very, very far away, you've actually got to go into the infrared to see all that action. That's the stuff that normally you would see at visible light wavelengths here in the local universe. Then you got to go to the infrared to see that same stuff happening in the very distant universe. And I think that that's going to be a
That's
real,
exactly right.
yeah, that's going to be a real
So,
benefit.
so, so one of the things we're interested in, I put another, excuse me, slide up
Oh, sure.
that you might want to share. We're very interested in the very early universe, how the earliest stars formed, how the earliest galaxies formed. And this image is a piece of what's called the Hubble Ultra Deep Field. This was an image taken with the Hubble Space Telescope by finding a very empty part of the sky. You have to remember that the whole field of view of the Hubble is like a grain of sand held at arm's length. That's how much of the sky you're covering. So a very empty piece of the sky was selected, and then the telescope took an 11-day long exposure. And that's, you're looking at a piece of that here. And these very faint red objects, and I've blown up 3 of them in these postage stamps, these are very early galaxies that formed less than 300 million years after the Big Bang. And you can see that they have a peculiar shape. You know, as you
Right,
look
yeah. They don't look
deeper
like
in the
proper
universe,
galaxies.
as you look back in time, as you look deeper in the galaxy, you're looking at galaxies that were early on in the life of the universe when they were just putting themselves together, and they look very different than they do in the current epoch, like the Milky Way. The Milky Way is a very well-developed
Hmm.
um, spiral structure. Galaxies, as they're first forming, look very different, and you can see these are very red because of the redshift that you were mentioning. You know, light that's emitted in the ultraviolet, uh, by very luminous stars, for
Get
example,
shifted to the red.
gets redshifted into the near infrared by the time it goes all the way across the universe. So, what's what's so interesting about having a large telescope on the ground is we can now go in with very high resolution and get spectra around these galaxies and understand what's going on in a way that we cannot do today with either a telescope in space or with the smaller telescopes on the ground. So these are very faint, they're very far away, and we're going to do
Imagine being able
terrific.
to see even more details and see the star forming regions and characterize the species of hydrogen and helium that are composing those stars. These are, I mean, what we're looking at in this image. Again, we're thinking about the fact these things are so far away. They are hundreds of millions, if not billions, of light years distant. We're looking at the light coming from some of the earliest galaxies in the universe. You're looking at the light from the very first stars, and to actually be able
Yeah.
to identify those stars and pick them out and see what they're made of and what their temperatures are like. How cool would that be? AJ was asking if adaptive optics excel in infrared, would GMT be optimal in reverberation mapping of active galactic nuclei? Boy, you know, I think yeah. I mean, I know my friend Mike Brotherton. He studies quasars and active galactic nuclei, and he actually does reverberation mapping. I bet that he's probably gonna be putting in a proposal for, or he should be putting in a proposal for GMT. What do you think, Jim?
Yeah, no, I would agree with that. Yeah, just about every frontier in astronomy we can advance with the Giant Magellan Telescope. It's a very general purpose machine with very capable spectrographic instruments. So, I think active
Hey,
galactic nuclei, absolutely.
there's Mike Brotherton. Mike, let me introduce you to Jim. Maybe he can hook you up with some time, buddy. We'll talk about that. Let's see. Wow, yeah, man, I would love to Skatoogle. I'd love to talk to the software engineers that work on the data processing. Yeah, I bet there's a ton of data work that has to go into getting this stuff ready. And let's see. Well, Arduino, I tell you, reverberation mapping does what exactly? You know something? I think we're going to have an astronomer that does reverberation mapping Mike, on the show sometime to talk about just that. I think we just hooked in our guy right now, and he's actually applying to Gemini right now to do some reverberation mapping. So maybe we'll talk about that. If you guys are into quasars, if you guys are into quasars, let me know in the chat. Quasars, yay! Quasars, nay! I want to know right now: are we doing quasars in a near future episode? Let's see. And thank you so much, Jakali. I messed up your name, and I apologize for that. But thank you so much for the super chat. Thanks for fascinating chat. Do more of these, please. You know what? I will just say that someone was asking, after the situation is passed and we're back in the planetarium, there's no need to do these anymore. Well, actually, we're going to continue to do these because we seem to have a lot of fun, and besides, we can bring people in from out of town. So anyway, I think so far the quasar talk is getting some love, and I think we definitely want to see. So Jim, I think we want to see some quasar data from GMT when it's all settled and when it's all set up and running. To that end, I have just one kind of quickie wrap-up question here, and that is, you guys have been working on this very hard. This has been a long time in the making, and you've talked about how it takes years just to cast a single mirror, and you're trying to make 7 + 1, an 8th mirror. So when would we hopefully see first light? When do you think our telescope would be ready to go?
Right. So that's the $40,000 question, so to speak. We are currently working to a plan to have what we call first light of the telescope at about the end of this decade. And the plan is to go on sky, as we say, with 4 of our 7 segments and do some early science capability and early science observations with that capability. That will already be a larger telescope than any telescope that exists today. And then in the early part of the next decade, in the 2030s, we'll finish out the telescope, bring all the adaptive optics modes online, and so on. So it sounds like a long time in the future, but I have to remind myself that these telescopes, in some sense, they connect us to the cosmos in and even in a spiritual way. They're kind of, for me, like modern cathedrals that were built to connect people to the cosmos. And it won't take 300 years to build this telescope the way it took some medieval cathedrals to get built, but you do have to be patient because they are very ambitious projects.
And I think they've got the right guy leading it. Jim, I would not want your job at all to be able to coordinate so many things. I know project managers they're the people who are responsible for making sure that everybody else gets all the credit, and they're always the one who end up taking all the blame when things go wrong. But it seems like this project is in extraordinarily capable hands, and thank you so much for building the Giant Magellan Telescope, Jim. Thank you so much. This is great. I hope that as GMT develops, that you consider coming back and maybe updating us and telling us a little bit more about what's happening with the telescope. Does that sound okay to you? I'm just putting you on the spot in front of everybody, so don't feel pressured to answer.
Sure, I'd enjoy coming back and giving you an update at any time that you're interested.
Oh, we'd love to have you back, and I want to thank you so much, and thank all of you for joining me today. Please join me in thanking Jim Fanson, Dr. Jim Fanson, for building the Giant Magellan Telescope. Give it a thumbs up. Give Jim and the GMT Observatory. By the way, Jim, where can people learn more about the Giant Magellan Telescope?
If you want to learn more about GMT, you can go to our website at www.gmto.org. And then you can follow us also on social media platforms. But start out at the website, and you can find a lot of very useful and even pretty technical information if you're interested in that.
There is a lot of incredible information. As a matter of fact, one of the first videos I made on this channel was about the Giant Magellan Telescope. So I'll have a link to that video in the comments, and feel free to check that out if you kind of want more of like a background primer. But honestly, you got it from the source himself. So thank you once again, Dr. Jim Fanson. And I want to thank all of you for joining me today. And I especially just want to take a second and just thank my Patreon supporters for helping to make Launchpad Astronomy happen. You guys are helping to keep the lights on. Also want to give a special shout out to my intergalactic level supporters and to my cosmological level supporters. And I just want to say that if you would like to help support Launchpad for the price of a cup of coffee every month, well, please feel free and check out my Patreon page. And above all else, if you'd like to join me on this journey through this incredible universe of ours, well, please make sure that you subscribe and ring that notification bell, there it is, so that you don't miss out on any new videos. So until next time, once again, my thanks to Dr. James Fanson. I invite you to please stay home. I know, we just got to keep doing it. Wear a mask, stay healthy, and above all else, stay curious, my friends. Until next time, good night.